More and more children are out of school, but parents don't want math learning to stop. They're turning to Mathnasium at home. Real-time math instruction tailored to your child's exact educational needs. It's the same face-to-face live instruction used in our centers for over 15 years, now on a computer. Your child can keep their math skills sharp, catch up, or soar ahead, from home or anywhere with an internet connection. To learn if Mathnasium at home is right for your child, visit mathnasium.com/at-home. Mathnasium at home, changing lives through math.
Hi everyone, and welcome back to Mathnasium Schoolhouse. My name is, as always, Sandra. I am your instructor for today, and I'll be with you throughout this lesson on Pythagoras' theorem. You might have heard this called many different ways: Pythagorean theorem, Pythagorean theorem, Pythagoras' theorem. No matter what you've heard it called, it's all the same. We are going to explore it today. For any of you that have maybe seen this in the classroom, hopefully, again, you learned something new, a more fascinating, more efficient way to solve some of the problems that might include this theorem. Welcome to everyone. I love it when you guys just are 10 steps ahead of me and already share with me your name, your grade level. Always wonderful to see all of that. And thank you for sharing the stream as well. If any of you would like to do that as well, get your friends and family members to also join in on this math conversation. We'd love to have them join, so go ahead and share if you're able to do so. And continue to let me know who we have here today. I see Srikar. Lovely to see you again. I love to see the familiar names. Hopefully you all are ready for today's lesson. I always recommend having a sheet of paper and something to write with, so go ahead and get that if needed. Today in particular, it might be super helpful to draw out some of these hint triangles that we'll be working with today, because of course, if you know anything about Pythagoras' theorem, it does involve right triangles. So it might be super helpful to really visualize what it is that we're saying today. As always, though, I will do that for you on my whiteboard also. Welcome, everyone. Oh, wonderful. Ivan, you shared. Thumbs up for that. Very good. I appreciate that. Wonderful. Also, let me know if you know anything about this theorem, if you've learned about it. It would have been during some geometry unit in the class. And if you did, what is it that you remember? What is it that you enjoyed? And maybe even any questions that you might still have on the theorem. And we can absolutely see how we can tackle them today as well during the lesson. So I am going to start off today by actually bringing your attention to a lesson that I had this Monday that just passed. And I did that lesson on perfect squares and square roots. And primarily, it's the square roots that I'm interested in just reviewing really quickly today. So if you joined, wonderful. You can help me in answering some of these. So I'm going to just review that lesson with some problems on my board right here. So as I write them, go ahead and share your answers for me in the comments. So here I'm looking for the answer once I evaluate 9, and I can say this so many different ways: 9 squared, 9 to the power of 2. And if you know what that means, then you also know that it is equal to this. So for those of you that maybe are not familiar with exponents, not a big deal. Maybe you can just tell me what this is equal to. And I apologize if you're not used to the dot as a way to represent multiplication. I just included the standard multiplication symbol there. So go ahead and tell me what that is. I also have here 5 to the power of 2 plus 12 to the power of 2. If you'd like to tell me what that is. I see some answers coming in. Wonderful. And then let's look at one square root before I kind of give you a few more. Square root of 169. And I'll give you just a few more. I see Rebecca replying, hello, and you said 9 to the second power, and it is 81. Very good. So I'm just going to write that down here. That is exactly right. 9 to the power of 2, or 9 times 9 is 81. Wonderful. That might be a fact that we might need today, but in particular, it's this fact here, that if you see this little exponent of 2, we know that we have to multiply that base number by itself. Which means I can take that over to this second question here. I don't think I've seen the answer just yet. So let's maybe take this a step further from what's written here, and I'll help you out. Well, I almost gave the answer away. 5 to the power of 2 is 25. And 12 to the power of 2 is 144. And so all that we require here is the sum. Oh, there we go. I do see the answer. I see 169 appearing, which is exactly right. Perfect. And then look at that, 169. What is the square root of 169? Let's see if anyone can share that with me. I'll give you a few more seconds to help me out. What do we have? Square root of 169. So remember, I'm looking for some number multiplied by itself gives me this whole number of 169. 13, there we go. I've seen it just now. Wonderful. Good. So we're going to have to use some of this knowledge today when working with the Pythagorean theorem. So let me just give you a few more review exercises. I love that we're all on the same page though. Okay. So let me also ask you, what is some number? So find this number that's underneath the square root when the square root of that number that you're looking for is 30. So how can I find this here? Okay. And I am also going to ask you another one where it's just 19. So again, I'll give you a few seconds to try to find that out. You can use some of the knowledge you learned from Monday's lesson, all right? Or maybe you just know it. Or you're using your sheet of paper to actually do this calculation. Regardless, share with me your answer. I actually see it appearing. All right, I'll take Rebecca's answer this time. So that's exactly right. So if I'm looking for what this question mark actually is, what number this question mark actually represents, I can find it using my knowledge on how to find the square roots of numbers by looking at this number here and knowing that this number multiplied by itself actually gives me this one here. And we kind of talked about that on Monday, where we said we can find the square roots of numbers, and the other way around, we can find the squares of numbers when they end in 0 really quickly. We learned some nice tricks for that, right? So I can approach this by taking 30 times 30 and performing the long multiplication. The funny thing is, I actually don't need to do that. I can do this really quickly, all in my head, right? So it is 900. I saw that number appearing. So let me write that in here. This is actually 900. And one of the tricks that we talked about on Monday was when we have a number that ends in 0, when you multiply it, you're going to have double zeros and then the square root of the number that's in front here, okay? So if you want to revisit that lesson, go ahead and do that. It was the one on perfect squares and square roots. And I can do a similar thing here with 19. I can absolutely go ahead and perform my long multiplication. I don't know about you, I'm not necessarily the biggest fan of resorting to long multiplication if I don't have to. And it does require me to write out a lot. So you can go ahead and do it. It's always great practice to do so. Or you can just maybe try to do that, try to find 18 squared, 17 squared, and move on to what you know, some facts that you know, and try to work your way up from there. So this one is actually, if any of you carried that out, yes, you did. I see it appearing, 361. And given this problem, I'm actually also going to review something that we talked about on Monday, which is to find the square root of a number that is not so friendly looking, it's not so pretty. We talked about rewriting this number using its prime factors, right? So performing prime factorization, and then seeing if those factors actually create a square. So here I can rewrite 361 only as, coincidentally, 19 times 19. 19 is a prime number. So it's fairly easy, but I promise we'll encounter some problems where we actually can use that knowledge to actually create squares today. But here it's as simple as saying, well, 361 is equal to 19 times 19, and so the square root of 369 is 19, okay? If you need help with that, I highly, highly recommend revisiting that lesson, which is available on our Facebook page. and going through the step-by-step process that we went through that lesson. Wonderful. So I promise I'll reference some of those from that lesson and from this review for today. And as I said today, we're looking at Pythagoras' theorem. And I said you might have heard this as Pythagorean theorem. I'll probably use a bunch of those combinations today, just because I don't think I ever stick with one. I even asked my husband, who has done a master's in math, what's his way of pronouncing it, and I got a completely different answer. So regardless of how you pronounce it, Pythagoras was a mathematician, is a very famous mathematician, if you know anything about your math history. Many years ago, about 2,500 years ago. And although he's famous for so many contributions to, of course, this amazing subject of math, the thing that he's most famous for is this theorem, which is named after him, and it talks about right triangles. So let's talk about a right triangle before we get into the theorem itself. I'm going to draw a triangle here, and maybe you want to comment for me why what I drew here, how do you know it's a right triangle? Why does this look like a right triangle? How about that? We'll start there. And I'm going to help you out by saying, you know what, I'm going to put this little square here. And we referenced this in a previous lesson. What do you think? Why is this a right triangle? Well, I've denoted here with this square, and if you've ever seen just an angle itself with this little square, that means we have a right angle. And if you want to help me out, okay, I like an answer that I see there from Tanya's account. I'll reference that in just a second. Good. Okay, I see the most simplest answer, which is the most perfect answer right now, because it has a right angle. That's exactly right. So here we see this is how we can display a right angle in any diagrams that we show in mathematics with this little square here. And as you guys are already helping me out already, this triangle has a right angle, right? A right angle. Good. I see someone helped me out and says it has a 90-degree angle, which is exactly what this right angle is. Perfect. So to summarize, oh, what a beautiful answer. And it forms an L. I love it. I love when you can just look at it visually and think, you know what, it forms a perfect L. That's how I know it's a 90-degree angle. A long line, I see it's a 90-degree angle and it looks like half a square. And when you add the other half, it makes a square. The other angles is 45 degrees. Oh, beautiful. I love the observation there. Wonderful. Thank you for sharing that. So we have a right triangle here because it's a triangle with a right angle. That is exactly the type of triangles that we'll be working with today. And these are the only triangles for which this theorem works. So let's keep that in mind, okay? So a right triangle is a triangle that contains one right angle, okay? And you might want to challenge yourself and think, well, why doesn't it contain two right angles or three right angles? Why is that not possible for a triangle? We're not going to explore that today, but I challenge you to think of that later today. If you have trouble falling asleep, go ahead and think about this. So go ahead and do that. We're going to use this terminology for today. The other terminology that'll keep on appearing today as we talk about this theorem and right angle triangles as a result, and you might hear me say right angle triangles or just a right triangle, both work. But the other terms that'll appear today are, we have hypotenuse, so I'm going to spell that out first. Hypotenuse. Okay. We have hypotenuse, which you'll notice, and I'll use my green here, is this side. Someone commented that it is the long line, and that is a great observation. It is the long line. It is, in other words, the long side of this right triangle. And in fact, what a wonderful observation, it is always the longest side in your right angle. But I think the best explanation or the best definition for a hypotenuse is that it is always opposite this right angle. Okay, so that's your best way to remember where the hypotenuse lies in your right triangle. It is always opposite the right angle. Okay, and then the other sides of these triangles, we're not going to leave them out. We're going to name them. We're simply going to name them as the legs of the right triangle. And they are the other two sides that you can think of them as touching this right angle. Okay? So just some words that we have to keep in mind as we explore this theorem today. So what I'm going to do, maybe take a last look at this image here. I'm going to erase this and draw 4 different triangles on my board, and I'll name them 1 through 4. And go ahead and tell me how about you tell me which triangles, so just list the numbers, have a hypotenuse. That's probably the easiest way for you to comment to help me out, okay? So I'm going to erase this. Which triangles have a hypotenuse? So there's triangle 1. Okay, I'm going to call this triangle 1. Then there is triangle 2. Actually, let me make that a bit better. Okay. Triangle 3. And triangle 4. Go ahead and only list out, oh, I apologize, that one's off the board. Let me draw that one more time. That's good enough. Only list the numbers of the triangles that have a hypotenuse. Which ones? So we just talked about what it means to be a right triangle. We talked about where a hypotenuse lies in those triangles. Where is the hypotenuse? Triangle 1 and triangle 4. That is exactly correct. Why is that? They have right angles, right? And the hypotenuse, I said, is always opposite that right angle. So we have the hypotenuse here and the hypotenuse here. We don't see any right angles in triangle 3. This one is obtuse, if you've heard that language before, to acute angles, I should say. And then this is supposed to be an equilateral triangle, if you've ever seen this notation, which means that it actually does not have a right angle. So perfect. We're all on the same page, I hope, when it comes to identifying right triangles and, as a result, knowing what a hypotenuse in these triangles is. Okay? So as I said, there was this mathematician who is now famous for one specific thing. And if you study math further, you will learn a lot more from this mathematician. Today we're going to focus on his famous theorem, which is the Pythagorean theorem. So let me just write that out in case you're interested to learn more. Research this theorem later. So this is the Pythagorean theorem. As I said in the title of today's lesson, I just used the mathematician's actual name, and I said this is Pythagoras' theorem. You might see it named other ways, so if you need more information, you can always research the different forms. So this theorem tells us, and I'll maybe say it out loud first, and then I'll summarize it algebraically on the board here. But it tells us that the square of one leg of a right triangle plus the square of the other leg of the right triangle is equal to the square of the hypotenuse. So let's draw a right triangle here. We already mentioned that we're only talking about right triangles today, right? So if I take the square, you know what? I'm going to make this smaller. I can show you this visually. If I take the square, quite literally, the square formed on this end of the right triangle, of the leg, and then I take the square here, it's actually going to be equal to the square formed with the hypotenuse as the base of this square. Okay? Hundreds of proofs on this theorem. We're not necessarily going to address them today. Another great exploration for you to do after today, reach out to your nearest Mathnasium and ask them to have this conversation with you. I highly believe that the instructors would love to talk about it. Another way that you'll see this displayed is if I name the leg of this right triangle A, then this squared has an area of A squared, if you know your area formulas. If I name the leg of this right triangle B, this squared has an area of B squared. And very, very similarly, if this one is a C, the area is C squared. Which means I can summarize this as, and I'm going to use my colors here, A squared plus b squared is equal to c squared. And that is what we will be working with today. Perfect. Someone shared that just as I finished writing. Wonderful. So some of you might have already seen this. So hopefully we can apply this to some problems today that maybe still confuse you, maybe still challenge you, or maybe you've just never seen before. But this is what we're going to be working with today. So let's see how this applies to a right triangle. So I'm going to erase this. All we need to remember is a squared plus b squared equals c squared. And if you say that enough, I promise you, it'll be stuck in your head forever. A squared plus b squared equals c squared. So let's say I want you to find a, b, and c. I'm going to give you a triangle. It is a right triangle. I'm going to tell you that this leg is equal to 8, this leg is equal to 15, and this hypotenuse is equal to 17. Okay? So if I were to prove the Pythagorean theorem on this right triangle, I would be able to absolutely say that my c is equal to 17 because c is always my hypotenuse. And my hypotenuse is always opposite my right angle, so c is absolutely equal to 17 here. Okay? Then I can look at a and b. I think I used the opposite colors. Let me actually stick with the same colors as before. So I have a and I have b. Now these can be one or the other. Okay, so we can always say that the vertical leg is always a. If that just is easier for you to organize in your mind, do it. But there's no need to because a and b are just the two legs of the right triangle. So I can actually say a is equal to 8 or 15. And then whatever I choose for a, b is just the other one. So I can still say that b is equal to 8 or 15. Okay? As long as you don't say both of them are 8 or both of them are 15. So let me just repeat that one more time. A and b simply are denoting the lengths of the legs of the right triangle, which means they are both this vertical side and this horizontal side. And so we don't always have to say that this is a and this is b. I can say this is b and this is a. Let's see an application of that. So I'm going to just show you a different triangle. Okay. Let's say I tell you that this is, we'll stick with the same thing. So we have 8 and 15. We don't know what c is equal to. Let me just use that in blue. How do I find c? Well, since I know from before, Pythagoras taught us that a squared plus b squared is always equal to c squared. He proved it for us. We don't have to bother proving it right now because he promised us that this is always true. He did all the hard work for us. Great. So we're going to use that to our advantage. I can say that 8, just for fun, I'm going to mix it up, is actually my b and 15 is actually my a. And what I want to show you is that it doesn't matter because I'm just adding them up. And if you have explored addition in depth, the order will not matter here. So to find my c, I need to find the sum of these two squares, which we reviewed earlier. Oh my goodness, you guys are helping me out. Thank you. Which we found earlier in our review. I'm going to steal the answer I see in the comments because it looks exactly right. 15 squared, if you want to do that on your page, is 225. 8 squared is 64. Thank you for sharing that. That is equal to some c squared. And as was shared, I think that's off just by a bit. So I'm just going to correct it. I did the math earlier. So if I do that, I get, well, let's even do it together. So 5 plus 4 gives me 9. 2 plus 6 gives me 8. And then I only have 200s. So I get 289 is equal to c squared. And then, I apologize for that. Then I would just need to find what c is equal to, which means I would have to take the square root of 289 to find my c, right? And we saw this in our review earlier today. Some number to the power of 2 is equal to 289, so some number multiplied by itself is equal to 289. I can do a lot of trial and error if I'm not too comfortable finding square roots. There's no issue with that until you're ready to work with square roots. Go ahead and do that. Or I can go back to Sandra's lesson from Monday on square roots and explore different ways to find the square roots of whole numbers. So I challenge you to do that. I will tell you here that the square root of 289 is not a pretty number, so you might have to do this by hand. Okay? Let's do maybe one more. I'm going to challenge you guys to do this. I'm going to give you friendlier numbers. So one more right triangle before we move on. The two legs are equal to 3 and 4, and I would love for you to show me what is c equal to, meaning what is the value of this hypotenuse? What is its measurement? Okay. I'm just going to help you out by telling you again what Pythagorean theorem says. You can use this. Okay. Not too difficult, right? I can say 3 squared. I know that that's 9. I know that. I've memorized it. 4 squared. I've memorized that. I know I shouldn't even say memorized. I've seen it so many times that I just effortlessly can recall that. Okay? And all of that is always equal to c squared. When I add that up, it becomes such a beautiful square because the square root of 25 is 5. All right? Again, just something that I've seen so many times that I can just pull that out of my brain just like that. Okay? You might have friendly numbers like this. You might have super large numbers. So I'm going to do this one fairly quickly for you just to apply Monday's lessons. So, and you might have the right triangle oriented the other way, but don't get scared, right? The same formula or the same theorem applies because it's simply a right triangle. So I'll do this one for you, right? I can say these are still the legs because these are not opposite the right angle. I'm still looking for the length of the hypotenuse. So I can say, okay, 15 squared plus 20 squared is equal to c squared. I can maybe perform log multiplication to find 15 squared. That is equal to 225. And actually, someone found it for us earlier. 20 squared, I know just like that because it ends in a 0. I know that that's going to be 400. When I add that up, I get 625 is equal to c squared. And this is where what I said earlier about the prime factors, we can actually use that knowledge here. 625 is actually equal to 5 times 5 times 5 times 5. So 4 of them if you saw. Did I hold that up correctly? Yeah. So I have, just a side note here, 625. Let's make that neater. 625 is equal to 5 times 5 times 5 times 5. I could pair up 2 of those. And my apologies again for using the dot. I know some of you might not know what that is, and that's fine. Right? And so I see that actually 625 is equal to 5 times 5 times 5 times 5. I know 5 times 5, I know it's 25, so I know that the square root of 625 is 25. So just a cool thing to be able to do to apply our knowledge of square roots. All right, wonderful. Let's see maybe some application here. So we've been looking for the hypotenuse this entire time, but we don't always have to be looking for the hypotenuse. We can actually manipulate the a squared plus b squared equals c squared to work to our advantage in finding the length of a leg. So let's say I have a right triangle that has a length of 15 here on one of its legs, and its hypotenuse has a length of 17. And let's say I want to find one leg. I'm just going to call it A just because. Okay, I could call it B as well. So I know Pythagorean's theorem tells me a squared plus b squared equals c squared. I know that I'm going to use it here because I'm working with a right triangle. So now I want to see, well, how can I manipulate it to find my A? Well, my first step, just from standard math practice, is to substitute what I have, right? Let me just work with the information that I have. Maybe something will pop up at me as to what I can do. So I know for sure that the hypotenuse is 17, is equal, the length is 17. I'm going to pop that into this equation here. A hasn't been found, that's my job to find, but B, the other leg, is found, right? I know that measurement. It's equal to 15. So if you're able to see this fairly quickly, if I want to find A, for now what I can do, and we briefly talked about this in one of the earlier lessons on solving basic equations, if I want to find this term, I can isolate for it, right? by bringing the 15 squared to the other side. So if you're comfortable doing that, I'll show that on the board in just a second. If you're not just ready for that, don't worry about it. You can play around with numbers, right? It's a step forward in understanding how to solve equations anyways. So don't be bothered if you're not able to isolate for a term in an equation for now. What you could do is find the square of these and play around with numbers such that this number plus this actually does give you 17 squared. So I'll give you those numbers here. So we have a squared would be equal to 17 squared, which is 289. 15 squared we've seen a few times now. And if I subtract these two, I get 64. And that's a beautiful one, because that's one that I have in my head already. I know that 8 squared, or 8 times 8, is actually equal to 64. So my other leg is equal to 8. 8 something. I haven't been told if this is centimeters or inches or feet or anything, so I'm just going to say it's 8. Okay? But you can see that the Pythagorean theorem allows us not just to find the length of a hypotenuse, right, the C, we can also use it to find A or B, which is pretty awesome. Okay? So what that tells you, in essence, is that given this formula, given this theorem, you're now able to do anything with triangles. And that is a superpower that Pythagoras has now given you. How amazing is that? So hopefully you encounter a lot of right triangles, because now you know exactly what to do with them. Okay, let's do maybe, let's see. I'm going to give you this problem here. I'm gonna challenge you with this. I don't have a right triangle just yet. I have a right, I'm not going to say a right rectangle. I have a rectangle. And what we know about rectangles is that they have right angles. That's just the property of rectangles, right? So I don't have to draw that. If I'm telling you it's a rectangle, you know that. But regardless, it has a diagonal splitting it in 2 pieces, okay? And what I want you to tell me is, what is the length of this diagonal if this longer side of the rectangle is equal to 12 and this shorter side is equal to 5. So make an observation first. Sandra just said this is a rectangle and that the diagonal splits it evenly into 2 pieces. Sandra also reminded me that rectangles have 4 right angles in every corner of it, which means that the rectangle actually splits, or sorry, I should say the diagonal splits the rectangle into 2 right triangles. So if you don't want to be looking at a rectangle anymore, we can remove one of the triangles and just look at this as a right triangle, right? Pretty cool, right? And this just comes from us putting bits and pieces together of what we know about these other shapes, these other things on our board here. And then it's just a matter of using Pythagorean's theorem, right? And it looks like I'm just looking for the hypotenuse of this right triangle. And once I find that, I've found the diagonal of this rectangle. And if I put some measurements here, I could put centimeters. For those of you that want to work with inches, I could put inches. It doesn't matter. It's still going to apply the same way, right? And I'll write this here. I could put 5 inches squared plus 12 inches squared is equal to my c squared. Very similarly, I'm going to find the square of 5. I'm going to find the square of 12, find the sum, then take the square root of that sum to find c. So if you guys want to write this down for yourselves and check your answer later, I'm going to tell you right now, this answer will be 13, oops, not centimeters, inches. Don't randomly change your units of measure, like I just did here. All right? Okay, there we go. So that's our hypotenuse, or I'm going to say one more time the diagonal of that rectangle. And you can always be given a lot more. And in the practice package that will be shared with you afterwards, there will be some more exercises similar to this. I'm aware of the time, so let's look at maybe just a few more observations we can make with the Pythagorean theorem. And one of them is called the Pythagorean triples. Simply put, they are 3 whole numbers that satisfy the Pythagorean theorem. So if I write here again, a squared plus b squared equals c squared, Any whole numbers that satisfy this, meaning if I add their squares, they're equal to c squared, are Pythagorean triples. The easiest one, the lowest one, the smallest one I should say, is 3, 4, and 5. You can maybe tell me why that is. 3 squared, if you want to help me out, is, well, 9. We saw this in the previous triangle, right triangle. 4 squared is 16. 9 plus 16 is 25, and that is in fact 5 squared. All right? Cool, right? And you'll notice that any multiples of known triples, Pythagorean triples, will also be Pythagorean triples, because if you know anything, if you've explored similar triangles before, all you're doing is working with similar triangles in that case. So those multiples of those triples that you know will also work. Okay? So let me ask you this question. I'm going to put a possible triple on the board, and I'd love for you to tell me if it is in fact a Pythagorean triple. Okay? And maybe as you're doing that, I'll just comment, the cool thing about just even being aware of Pythagorean triples is that it minimizes how much work you have to do in calculating to find a leg, to find a hypotenuse, right? If you know some of your triples, and I'm not saying to sit there and memorize them, but if you've encountered them multiple times, be aware of these same triples that appear up, over and over again, because they'll be so ingrained in your mind that when you come across them in another problem, you'll just be able to know what that other number is in that triple. So let's say I ask you, is 16, I'll give you a few seconds to think about this. Is 16, 30, and 34, are these three numbers altogether a Pythagorean triple? Do they form a Pythagorean triple? I'll give you a few seconds to think about that. It might be more apparent than you might think. Remember what I said about similar triangles. Okay, so possibly what you might be thinking is, can I reduce these by the same amount, get to some lower numbers that I can prove if they form a triple or not? Let's see if I can, right? So maybe if I just divide simply by 2, so 16 divided by 2 gives me an 8. 30 divided by 2 gives me a 15. And 34 divided by 2 gives me 17. Do I know if this forms a Pythagorean triple? I could check, right? I can go ahead and check 8 squared plus 15 squared, see what that gives me, and see if it does give me, in fact, 17 squared. Okay? And I'm going to tell you right now, if you want to try it out, go ahead. It does, in fact, form a triple. But notice what I didn't have to do is take 16 squared plus 30 squared and see if it equals 34 squared. I love math, I love numbers, but I am going to try to minimize how much work I have to do if I can, right? And when we're equipped with the tools in math, that's exactly what we're allowed to do. Cool, you remember triples from school? Very good. I'm glad that your teacher brought it up as well. It's a wonderful observation to make. Anywhere we can reduce how much work we have to do in math, I hope we learn that, right? It's the cool thing that Mathnasium does for us all the time. It's a wonderful thing. Let me leave you with one challenge before I let you go. So I'm going to ask you, what is the area? So we've talked about area before on Mathnasium Schoolhouse. What is the area of a right triangle? In fact, I didn't even have to write that it's a right triangle, but too late, I did. That has a hypotenuse of 5, and one of its legs is equal to 4. It's always so funny when I say the leg of a triangle. It almost makes it sound human or like a creature. But given this information, how can I find the area of a right triangle? I'll give you a few seconds to think about that. So this is really putting together a lot of different skills that we might have up in our minds. So go ahead, mathletes, try this one out before we end for today. So the hypotenuse of this right triangle is a 5. You might choose to use your piece of paper to draw this out. Do not worry if you have to. Some of us are wonderful at visualizing up in our minds. Others have a more difficult time, but it's no issue. That's what paper is there for, right? Okay. Okay, I see some thinking going on. I like it. I like where you're going. Okay. So the first thing we'd have to do is think, how do I even find the area of a right triangle? Well, it's just a triangle, right? The area of a triangle, if it's a right triangle or not, is still the same. It's base times height divided by 2. And if you need to remember why that comes about, go ahead and check out one of our previous lessons on the areas of 2D shapes. So the area of a right triangle, I'm just going to include this here, is base, let's see if I can fit this in, times height. I won't be able to. Let's do this. Base times height divided by 2. You might have seen it written different ways. It's all the same, so don't worry about that. And I can draw it out. I'm going to try not to, because what I want to just understand is if I have a base of my triangle and it's a right triangle, that base will always be, to simplify it the most for myself, one of its legs, right? And so I saw some of you thinking about that already. I can call this the base, but then the height will be that other leg that touches the right triangle or the right angle. But I don't have that. I've only been given one leg. So what can I do to find that other leg? Oh yeah, I can use the Pythagorean theorem to find that other leg. So I can say here that 5 squared is equal to 4 squared plus, I can call it A or B. Let me just call it the height. I'm not going to use H. I don't want you to confuse that with the H of the hypotenuse. So I'm just going to write out the word height. But I can find this, right? And so I can find 25, which is 5 to the power of 2, or 5 squared, and subtract 16, which is 4 squared, or 4 to the power of 2, and then find the square root of that. Or, what did I tell us about the Pythagorean theorem, right? Here, I actually don't have to do all that work, because I actually know that if I have a 4 and a 5, the other number that forms this triple is a 3. Look at that. Look at Pythagorean triple is helping me out here. So this is actually just a 3. Right? So I know that the height is just a 3, which means, going back to this, I'm just going to say it out loud here, the base, if it's a 4, right, and my height is a 3, if I divide that by 2 after I multiply it, what is it that I get? Let me see if I can see that appearing. Oh, I see it once. Yeah, very good. Okay. It's a 6. And it's 6 something. I didn't tell you what the units of measurements here were. So some of you wrote units. I love it. If you don't know what it is, go ahead and tell me that it's just units. And it's units squared because we looked at finding the area. All right. Perfect. I am going to end it there with maybe just a few words of what it is that we learned today. So we really did apply what we knew about square roots. So if you're fascinated in learning more about how to find square roots without turning to a calculator, I highly recommend you take a look at that lesson from Monday, because as much as we worked with whole numbers here with the Pythagorean theorem, just to simplify this, what might be this initial presentation of the Pythagorean theorem for some of our viewers, you're not always going to encounter beautiful whole numbers. You're going to encounter having to work with decimals and square roots of numbers that don't give you a whole number back. So go ahead and explore that and see how you can still apply that to the Pythagorean theorem, whether it's simplifying a square root of, or finding that decimal value. So go ahead and do that. There are countless proofs of the Pythagorean theorem, as I said earlier, and although I don't want to go through it here today, you can explore this on your own if you have shapes at home. So if you take a right triangle, form squares around it, so I'm just going to show parts of it here, and prove that if you take the area of these two squares, it forms the area of a bigger square, which I can't form here fully, but the bigger square that would be formed here, right? So go ahead and manipulate it to see that this red and this blue piece, these blue pieces actually form the area of that square. That's one way you can do it. I also don't have a big enough geoboard, which is what these things are, to prove it as well, bigger, but I have been able to prove it with a smaller amount, right? So you can see maybe I'll use my marker here, my right angle triangle here. It's a very, very tiny one, but I was able to form one square on this leg, one square on the other, and I would want to prove that those two areas actually form this square here. So those are two visual ways you can play around with the proof and prove it for yourself. There are some very creative ways out there in the real world that involve filling up with water as you turn a device that fills in the areas of these squares. And then other cool ways for all of you that really love algebra out there, which I'm definitely in that group, you can prove it by looking at cutouts of a square and triangles within bigger squares. So here, for example, you would be able to say that the area of this bigger square, which is just its side length squared, is actually equal to all of the areas of these 4 triangles and this one square here. So I'll start you off if you choose to explore that. So there are 4 of these right triangles here. So 4 times the area of a triangle would be base times height divided by 2. And add the area of this squared here, which you can see the side length is equal to this longer side length minus this smaller one, which is just b minus a squared. Okay. Really cool proofs. Like I said, hundreds out there. Have fun with them. You can be there all day researching, and if you're curious, do so. There's many word problems, which I'll share with you in a packet. You can apply the Pythagorean theorem to 3D shapes. So many things to do. I hope you guys had fun. I hope you learned something new today. We will see you all tomorrow. I love doing these lessons with you. I love seeing you guys join us back again. Have fun. Have a wonderful day, and we will see you again. Bye-bye.
It's afternoons that seem to be the most hectic for us, so it was much more convenient when we found Mathnasium at home.
All right, so how do we do half of 5? I think one of the best things about at home is that it really feels like you're almost at home with the student in their house teaching them.
I'm in my comfort zone.
You can just ask for help and the instructor will come right to you.
With Mathnasium at home, I know that they're getting the help that they need.
Awesome, great job.
Mathnasium, changing lives through math.